Well, good morning, everybody. Today, I just want to remind you, there's going to be no class tomorrow, conflict. But instead, what we're going to do is have a video. I'll send a link to a replacement lecture put together later today, after I know how far I get today. And you can watch that. Bring questions on Thursday, because maybe you'll get some questions, and we'll begin it at the beginning of Thursday, discuss any problems or whatever you want to discuss on Wednesday's lecture. Okay. Well, if you're wondering why I'm running on this side of the board, it's because the equipment is out again and I can't project up here like I wanted. So I don't get to do today's beginning talk. I was going to talk to you about a mathematician named Abel, who lived in the 19th century, contemporary for a while of Gauss. He only lived to be 26 years old. He's the guy who invented Abel's and came up with Abel's impossibility theorem, that you can't write a finite algebraic formula for the zeros of a polynomial greater than fourth degree, for instance, and lots of other things he came up with. He came up with some elements of group theory in algebra, which are quite advanced. Pretty young guy. You hear of abelian groups, also called commutative groups, named after him. Unfortunately, he got tuberculosis, and in those days he died young, so he didn't quite even make it to 27. He had just gotten appointed this prestigious position at a university. He died before he got the notice, I think. So unfortunately, I mean, tuberculosis was the #1 killer in the United States at the beginning of the 20th century. Actually, the average lifespan in this country, I think, was about 48 when it turned 1900. And so you can see it was quite a destructive influence in society. Well, took away poor Abel before he could be the brilliant mathematician he might have been. Today we're going to talk about, I'm sorry I didn't get to show you the pictures and stuff. We're going to talk about homogeneous linear second order differential equations. This is actually a really important topic. It sounds like such a narrow group of equations, right? Who would need homogeneous linear second order differential equations? But actually, those are some of the most important ones. And the theory behind them is quite beautiful. It's always hard to pull that out of the textbook too. So I hope one thing you'll get out of today is a feeling for how beautiful these solutions are, because what we've done so far, if you look at differential equation 3 for first order equations, basically all equations funnel down into an integration, right? And then you got an arbitrary constant, you got an infinite set of solutions with the constant as parameter. And so everything boiled down to integration. Actually, these linear homogeneous things and the linear non-homogeneous ones can be done by a way other than integration. How about that? And it's the major method. And like I say, these linear equations are the most important ones in science and engineering. And so hopefully you get an appreciation for some of those. And by the way, this is a different homogeneous than we talked about for homogeneous first order equations. Remember, a first order equation was this one, y prime. This isn't second order either, but this is called a homogeneous differential equation because it's homogeneous. The f over here algebraically is a homogeneous function in x and y, in the sense that if you replace y by ty and x by tx, you get the same result because the t's cancel. Any function where if you replace x by tx and y by ty, it's equal to itself, is said to be homogeneous in degree 0. So those from an algebraic from that point of view of homogeneous functions, this was called a homogeneous differential equation. It's not this concept of homogeneity. It's the following concept, a second order equation. We have to have y double prime first. Is linear, we said, if expressible as a function of t squared y dt squared plus a function of t y dt plus a function of t times y equals a function of t. We did this before. I just want to remind you because we're going to narrow it down. We're going to start with this and then see what subset this is of these. Now we'll say, generally, we're interested in standard form. We want to divide through by A of t because it has a better existence uniqueness theorem in standard form. But we'll say it is homogeneous, hence a homogeneous linear second order differential equation. If the right hand side is 0, isn't that easy? It's homogeneous. F of t is the 0 function. I'll write 3 equals. What does that mean? 3 bar equal. That means identically equal to or equal on the whole interval. So it doesn't look like I'm solving f of t equals 0 for one value of t. It means this is the 0 function. Okay. That is f, it's expressible as equation 2 here. A2 of t, d squared y dt squared plus a1 of t, y dt plus a0 of t, y equals 0. Generally, for existence and uniqueness of initial value problems, like we did last time, where you had 2 initial conditions to this, we prefer to put either of these standard form by dividing through by a2 of t. To get the non-homogeneous equation, we can call that 1a in standard form as d squared y dt squared plus t of t y dt. These have become kind of standard letters in most textbooks, p and q. So I'm going to write it this form, plus q of t times y equals, we could call it g of t. Maybe I should call this one g of t. Now let's call this one g of t. Just thinking about my letters, it's easier to understand. That can be g of t, and then this one will be f of t. Because I'm trying to stick to the standard letters for the standard form. So non-homogeneous equation looks like this, and a homogeneous equation, you just put 0 on the right-hand side. So that's this homogeneous, means 0 on the right. And then you only look at these on an interval where a2 of t isn't equal to 0 is what happens. So meaning, there's no point in the interval, where A2 of t is 0 in the solution interval. So we're going to look at the equations in this form. And then there's a nice bunch of results that are theorems that are fairly easy. So I better move this. By the way, I guess while I live, give you a chance to write if you're writing this down. I should mention, if you're having trouble online and want to come to class but registered online, I don't have any problem with you coming to class. We have lots of seats and everybody can spread way out. If you're in class and prefer to go home, worried about the new Delta variant, or just have a reason to be at home because you're a kid or something, you're welcome to do online too. I won't hold you to show up for lectures, but you can show up either place, everybody. I'm not worried about it. Small enough class, doesn't matter. So any questions on this so far? All right. All right, so those will be homogeneous equations. Now, what are we gonna, non-homogeneous equations?
Dr. Stapleton, I have a question. The definition of homogeneous, where it's for the first order, is that the only time that it gets that special definition, or is it that this definition still applies and that when it's first order, it just happens that f of y over t or y over x? It just
I didn't say it very well. I think this is a completely different concept of homogeneity. It's a different, like words have different meanings in different constants, in different contexts. What's a good example? Can't think of one now. But it's a matter of the word homogeneous meaning a different thing in different contexts.
Okay, that makes sense. I just wanted to check.
I mean, the best example I can think is in English, the word great. It can mean large, right, really big, or it can mean something's good. But they're sort of related because something's good is big in happiness or something. But so you can say great, it doesn't mean something's big. It means you liked it. And just so here, the word homogeneous here means that if you replace x by tx and y by ty, it's a function that's homogeneous of degree 1, meaning the t's will cancel and you get back the same function. F of ty, f tx is the same as f y xy. So I'm spending too much time on this. So a function is homogeneous in general of degree k if f of tx, ty is t to the k, f of x, y. That's a functional analysis concept. So this is a homogeneous differential equation. The first order is an equation in which the right-hand side is homogeneous if degree 0. It's t to the 0 times this, or just 1. And this concept is completely different. It means 0 on the right-hand side. There's a broader way of saying that. So yeah, I'm sorry. I hope I didn't spend too long on that. And the point is, it's a completely different meaning of homogeneous. All right.
Thank you.
Yeah. So now, here's a first theorem. What's neat is this carries over to other things besides differential equations too, this idea of homogeneity. If y1 of t and y2 of t are any solutions whatsoever of a homogeneous linear equation, 2a, well, actually of 2.
Can you move the camera a little bit?
Yeah, I didn't get it over far enough, did I? Thank you. Two A is a special case of 2, so I'll say including 2A. Then so is a function, a constant times y1 of t plus another constant times y2 of t for any constants whatsoever. So I'm gonna close this. I don't know if you hear it online, but that blower they have in the hall is really making it hard to hear. All right. Sometimes the sound system cuts that out nicely. I don't know what it's doing right now. So that's an interesting thing. We call this a linear combination of solutions. If you have taken linear algebra, you've heard linear combination before. Anyway, if sometimes in physics they'll call it a superposition of two solutions also. The idea is if you have solution, any two solutions, you can take a constant times one plus a constant times the other, and it's still a solution. And then you can extend this, maybe a lot of you are already thinking this, if you had a constant times one plus a constant times another plus a constant times another plus a constant times another. Any multiples of solutions all added together is again a solution, just by extending this, right? So we can consider this example just to show you. And the proof isn't hard. Maybe we should do it. Let's do it just to see why, because actually this, then you see why this extends to other topics. Use proof for 2a, because that's the one we're interested in. Everybody writes their second order homogeneous equations in the standard form. Proof for 2a. If y1 and y2, I'll suppress the of t just to save writing, are solutions of equation 2a, then you put it in. You put in the derivative of c1y1 plus c2y2, where c1 and c2 are constants, but y1 and y2 are functions of t. I just didn't write the of t on there. Dt, t squared dt squared is equal to plus the derivative of c1 y1 plus c2 y2 with respect to t times p of t plus q of t times c1 y1 plus c2 y2. So what I'm doing is I'm putting c1 y1 plus c2 y2 into the left side of the differential equation 2a. Then what happens? The second derivative of a sum is the sum of the second derivatives, and the constants come out. So I rewrite this as c1 d squared y1 dt squared plus c2 d squared y2 dt squared. Just by calculus, right? The derivative sum is the sum of the derivatives. You can pull the constants out. That's all I'm doing. Plus p of t times, and then I do the same thing here. C1 dy1 dt plus C2 dy2 dt, and plus q of t times c1 y1 plus c2 y2. And you regroup these now. All right, well, I'm going to take this one and this one and this one and group them together. And then I've got c1 d squared y1 dt squared plus c1 p of t y1 dt plus c2 c1. Oops, this isn't c2 there. Sorry. Plus, oh no, that's right. Plus this one q of t c1 q of t y1. And then I'll group all the terms with y2 in. C2 second derivative of y2 plus c2 p of t 2 dt plus C2 Q of Ty. And now you can pull the constants out. This one is all just C1 times, right, Y1 double prime. I'm running out of room, so I'll sort of abbreviate my notation here too. Plus P of T, Y1 prime, plus Q of T, Y1. So I factor out the C1 from these. And then I go over here and I factor out the C2 from these. Y2 double prime plus P of T, Y2 prime. Maybe you can see it now. Because Y1 and Y2 are solutions, this is equal to 0, right? And this is equal to 0 because Y2 is a solution. Y1 is a solution, that is parentheses 0, Y2 is a solution, that one parentheses 0. So we got C1, this is equal to C1 times 0 plus C2 times 0. The whole thing adds up to 0, which is the right-hand side. So you put this in the left-hand side of the thing. But this is equation 2, right? If you now call this Y, it says you put Y in the differential equation and it satisfies it. So that's the, I'll tell you what that means, QED. Stands for, it's Latin, stands for quod, I think. All right, erat demonstratum. If you ever see that in proofs, not as common as it used to be. Latin, it means which was to be shown. Just maybe completed your proof. Anyway, that's what QED means when you see it in that textbook. Probably more popular when Euclid's The Elements was still being used. All right, so now an example. Suppose I have this one, Y double prime plus 4Y equals 0, right? Here's a second order homogeneous equation with constant coefficient. Or the homogeneous second order equation in standard form. So now we by plugging in, you can see that Y1 of T equals sine of 2T is the solution, right? Y1 prime is minus 2 cosine. It's 2 cosine. And Y1 double prime is minus 2 sine 2T. And you plug that in, and so Y1 double prime plus 4Y1 is then, that's, let's see, minus 2 sine T. This is not minus 2, this is minus 4 by the chain rule. And so I get minus 4 sine 2T plus 4 sine 2T was Y1 plus 4 times Y1 was sine 2T. So you just plug it in to the left-hand side. Here's Y1 double prime, here's 4 times Y1, and oh, they cancel, you get 0, right? So Y1 is a solution. Similarly, you can plug in Y2 of T equals cosine 2T. And you can kind of see the root of cosine 2T is minus the sine of 2T, and its derivative is minus 4 times the cosine of 2T. So I'll just write it down. Y double prime is then minus 4 cosine 2T, but it's simulated by the chain rule. To observe that y2 of t equal cosine 2t is also a solution. Therefore, by our theorem, if I take 2 sine 2t minus cosine 2t, I know immediately it's a solution, right? Because it's a number times one plus a number times another. I just proved that there'll always be a solution. Or I could take 5 times cosine 2t, 5 times one and 0 times the other. That's a solution, right? Or I could take square root of pi times sine 2t minus e times cosine 2t. I can take any multiples I want whatsoever, and there'll always be a solution. This only works for homogeneous linear differential equations. It doesn't work in general in differential equations. So just when it's 0 on the right-hand side in a linear equation, that's it. I didn't move that too soon. All right, now, next concept is linear independence. If you've done vectors from calculus before, if you remember those, maybe you talked about linearly independent vectors before. This might make more sense. But in any case, we'll just start it from scratch for functions now. Definition. Two functions. Let's say y1 of t and y2 of t are said to be linearly independent. Again, if you have linear algebra before this class, this is probably obvious, but it's not so obvious. But it's said to be linearly independent if on an interval. In our case, we're looking at the solution interval. If C1 times y1 of t plus C2 times y2 of t identically equal to the 0 function on the whole interval has only the solution C1 equals 0 equals C2. The only way you make this equal to 0 on the whole interval is make both those constants equal to 0. Okay, ask questions if you have them. That's part of the good thing of coming to class. Maybe that sounds familiar to something. Here's the analogy with vectors. Really what this means, if you think about it, for two functions, is that one function can be written as a multiple of the other, right? You subtract this one over and divide by C1. And as long as C1 isn't 0, that means that Y1 is minus C2 over C1. So it's a multiple of the other one. Or you can subtract it the other way, makes Y2 a multiple of Y1. So for two functions, this just means one is a multiple of another. We couch it in this language because for more than two functions, it's harder and need this definition. But here's the analogy. You can also do this with vectors in the plane. Two vectors, v and w, are independent vectors of the plane, Euclidean plane, if C1V plus CQW equals the zero vector, has only the solution C1 and C2 both equal to zero. And so you can think of it this way, vectors at the same point is the idea. Vector V and vector W. I can't take a multiple of this vector plus a multiple of this vector and ever get the zero vector, right? Because once I move out in this direction some length, maybe there's half this vector, plus I'll add this vector. I got at some point other than the origin. We call them linearly independent, unless they're pointed along the same line. So these are independent. If they happen to be pointed along the same line so that they're multiples of each other, now you can take, here's vector V, and here's that vector W. Maybe you can take W minus twice V, if it's long, equals the zero vector. Sure enough, these are dependent. So these are independent. You can't make a zero vector by adding a multiple one to the other and get the zero vector. Now what you observe just geometrically is you can only do this if they're lying along the same line, right? So one's a multiple of the other. Same thing here, it's just in function space instead of in vectors. And what that means really is, this is sort of an abstraction, what you do with vectors. We're now dealing with a vector space of functions. I'll say the two functions is abstract, in a abstract vector space are dependent if one's a multiple of the other. So that's the context. Maybe that makes it seem a little more like something you've seen before. You might think this next test is kind of silly because if you just have to check if one's a multiple of another, why do you need this complicated test? The reason is that in more dimensions you need this test. If you just have two functions, it's easy to see if they're dependent, just if one's a multiple of the other. But if you have three or more functions, it's not so easy. So we'll say this: the Wronskian of a set of functions, y1 of t, y2 of t, again on an interval, is this determinant w of y1, y2, I'll suppress the of t in here, is y1, y2, y1 prime, y2 prime. The two functions followed by their two derivatives put into a 2 by 2 determinant. Remember from calculus what this determinant means? What does it mean? If you took linear algebra, again, this is real easy, but most people don't before they take this class. But enough do, I always mention that. The determinant means just take this times this minus this times this. Remember that? So that's all it means. It's a short notation. It's not really short, but it's another notation at least. So diagonal, this diagonal minus this diagonal, right? This one times this one minus this one times this one. That's the Wronskian of two functions. The reason we introduced this klutzy notation is it helps us to generalize when we have more than two functions again. So even though this stuff seems like a lot of overkill, it'll help us to generalize later. I think it was the great Gauss who said we must always seek to generalize, right? So let's follow that. The Wronskian now has this theorem. If y1 and y2 or 4, let's say, y1 and y2 solutions of a homogeneous linear differential equation, 2A or 2, it doesn't matter. With P of t and Q of t and f of t continuous on the solution interval. I'll stop writing that, it's too much work. It's supposed to be understood. Y1 and Y2 are linearly independent. Sometimes I'll just say independent, meaning the same thing. People get tired of writing those long phrases. Are linearly independent if and only if their Wronskian is not equal to 0 on the whole interval. But, and the other possibility is that they're linearly dependent. I'll leave off the word linearly. If the Wronskian is identically equal to 0 on the whole interval. How about that? This is a theorem due to Abel. Like Abel. Presumably pronounced it Abel, I think. The proof is in the notes if you're interested in it. It's long. I don't care if you know it or not, but if you take the interest as a math major, you can take a look at it. Tacitly written in here, if you think about it, is that the Wronskian of two solutions of a linear homogeneous equation is either 0 on the whole interval or not 0 on the whole interval. It's not 0 at some places and non-zero at the other. For two solutions, it's either 0 on the whole interval and the functions are dependent, or it's not 0 on the whole interval and they're independent. Now, this has a more general result also. I'm going to extend this from Abel's theorem. More generally, we'll say for general functions, not necessarily solutions of the differential equation. See that maybe? Yeah, I guess. Y1 of 2, Y1 of t and Y2 of t, not necessarily solutions. You can still say some interesting things that you might see in other classes, so we'll point this out even though we don't need this part for this class. Not necessarily solutions of 2A. If the Wronskian is equal to 0 at any point in the interval, or excuse me, it's not equal to 0 at any t, then Y1 and Y2 are independent. It's actually important to introduce this because this great result only applies to solutions of the differential equation. More generally, there's still this nice result that if you can show that at any point the Wronskian is not 0, then they're independent. However, in this case, for general functions, the Wronskian might be 0 at some points and not at others, or it might be 0 on the whole interval, and then they're still independent, it turns out. Equal to 0 does not imply that they're dependent. So the Wronskian, Y1 and Y2, identically 0 on the whole interval, does not imply dependence. And the Wronskian doesn't have to be 0 on the whole interval either. So the Wronskian has utility outside of this class, but it's not as interesting because it's more complicated and doesn't show as much. This is a really beautiful result here because the following thing, let me know if you need me to move that back for a second. Last result wasn't as important, so I didn't keep it as long. Here's the big granddaddy theorem now. Actually, you know what, let me do one more thing first. I need an example of that, sorry. The Wronskian of the two functions sine 2x and cosine 2x that we did, all right? What do we know about the Wronskian? We want to actually compute this so you can do your homework, right? The Wronskian, you just put the functions on the first line and their derivatives on the second line, their first derivative. So this would be 2 cosine 2x, the derivative sine kx. Remember this formula I said you had to memorize this semester, also for the exponential function. So sine kx is k cosine kx by the chain rule in calculus, and the derivative of cosine kx is minus k sine kx. So we're just going to use those rules immediately and not do a chain rule every time. Derivative of cosine 2x is minus 2 sine 2x. So there's the Wronskian is this determinant. And remember how to do the determinant. You take this times this, minus this times this. So it's sine times minus 2, sine 2x times minus 2 sine 2x is minus 2 sine squared 2x. And then minus this times this, 2 cosine squared 2x. Well, let's see, that's just minus 2 times sine squared plus cosine squared of 2x. And then you remember your trig identity, sine squared plus cosine squared is 1, so this is equal to minus 2. Sure enough, it's not 0 in the whole interval. In this case, it's equal to a constant on the whole interval. That's not necessarily the case for other functions. What does that tell you when the Wronskian is not 0? It tells you that sine 2x and cosine 2x are a linearly independent set of functions. Or we'll just say they're linearly independent. Or we'll just say they're independent, short, because I get tired of writing. Right? So those are independent functions. You might have thought, how can those be independent? They're kind of like vectors. They look the same, you know. The sine of 2x, for instance, looks like this, right? Right here completes a period at pi. The cosine 2x is exactly the same shape, just shifted over. How can those be independent? In fact, they are according to this definition. So they're not a multiple of each other. They shifted over, makes them independent. Actually, you just go to this definition. But here's the thing: you think that one's not a multiple of the other, but how do you actually prove it? Here's a way: use the Wronskian. The Wronskian proves that they are in fact independent. Right? Sometimes when you get more than two functions, you want to do this kind of thing. I want to just mention in passing that this applies to higher numbers of functions. Note, similarly, 3 functions, y1 of t, y2 of t, y3 of t, and you can go any number of functions, are independent. If what? Meaning linearly independent. If the equation c1y1 plus c2y2 plus c3y3 equals 0 on the whole interval has only the solution c1 equals c2 equals c3 all 0. You can't put any constants in there and make it 0 on the whole interval. Then they're independent. But otherwise, they're dependent. Now you see the utility of the Wronskian. It extends by a similar theorem, a theorem with a similar proof. that says, if the Wronskian of y1, y2, y3 is not equal to 0 at some point, then these functions form a linearly independent set on the interval. Always has to be on some interval. This is important here because of three functions, it's hard to tell if they're linearly dependent. They're not just necessarily a multiple of each other. It's like vectors in three space. It's harder to tell if they're dependent than in two space, right? In three dimensions, you can imagine three different vectors. How do you know if these are dependent? It turns out dependence, and maybe you've seen this before with vectors or not. But three vectors are dependent if they all lie in the same plane, right? Because you can take a multiple of this one, maybe go out here, and a multiple of this one out here. And a multiple of this one plus a multiple of this one adds up to this one, so you can make all three of these cancel. So it's hard to tell with three vectors in three space whether they're dependent. You have to see whether they lie in the same plane, and that's not so easy, right? But the Wronskian does it, but you can do a determinant with vectors and check it out. And you put the three vectors into a determinant, that if the determinant is 0, they're dependent. If it's not 0, they're independent. Similarly, three functions can be really difficult to find out if they're dependent. For instance, suppose I gave you cosine squared t and sine squared t. And cosine 2t. Are those dependent or independent? None of them is a multiple of the other. This one's shifted. It's 1 minus that one. Right? But are they dependent or independent? Well, if you were to take cosine squared times 1 plus sine squared times minus 1, and then subtract and then add minus 1 times cosine 2t, you get 0, right? Because cosine squared minus sine squared is equal to cosine 2t, right? And so this is equal to cosine 2t. These subtract out and cancel and give you the 0 function. These three functions are actually dependent. You can take 1 times this one plus minus 1 times this one plus minus 1 times this one. Multiple of one plus a multiple of another plus a multiple of another is 0. And see that these are dependent because you make the 0 function as a linear combination of these three. So this is complicated stuff, and we're not going to do the third order equations. I just wanted you to see what independence means. Two vectors in the plane are dependent if they lie on the same line. Three vectors in three space are dependent if they lie on the same plane. We're thinking of the same concept with functions here. If a function is a multiple of another, those two functions are dependent, but for three functions, it's harder to tell. It extends this concept. Three functions lying in the same plane of functions is hard to tell. So what you do is you go to the Wronskian for the Wronskian will tell you because now the Wronskian of three functions is a 3x3 determinant. You saw those in calculus too, right? When you took cross product and so forth. The Wronskian, I just want you to see the generalization here. Y1, 2, Y1 prime, Y2 prime, Y3 prime, Y1 double prime, Y2 double prime, Y3 double prime. So the Wronskian extends actually to more dimensions. And if the Wronskian is not 0 in the interval, then you know these are independent. And there's a similar theorem for third order equations with Wronskian that's got three functions. Anyway, so that's just to give you an idea for what linearly independent means, and to make you realize that in more dimensions you need the Wronskian. You can write a 3x3 determinant for three functions, a 4x4 determinant for four functions, etc., and determine if a whole lot of functions are independent or not when it's real hard to tell geometrically. Any questions you want to ask on that? That's pretty difficult stuff, really. The important thing is this. If, the one we erased, I guess, with two functions. For solutions of a differential equation, that they're linearly independent if and only if the Wronskian is not zero the whole interval. And they're linearly dependent if and only if it's equal to zero the whole interval. All right. Now, why is this such a big deal? Here's the granddaddy theorem I started to put before. The differential equation 2a, it only applies to these. It's the linear equation with homogeneous equation. D squared y dt squared plus, and we p of t, and by the way, we do now need the standard form. This doesn't necessarily apply to the other one that's zero on the part of the interval. Plus p of t dy dt plus q of ty equals zero. Let's remind you what 2a was. Has general solution. And the general solution means it's all solutions. But in particular expressed as a linear combination of two solutions. So we're going to write down every solution of this differential equation. Y equals C1 times Y1 of t plus C2 times Y2 of t. That's all solutions to the differential equation. We can call this 3. Where Y1 of t, Y2 of t is any linearly independent set of solutions. Okay. And it's such an important concept. It's fundamental, right? We'll call such a set a fundamental solution set. If you have a set of solutions of two solutions to a second order equation that are independent, we'll call them a fundamental solution set. Okay. That says that all you have to do to find all solutions to a homogeneous equation, and I forgot to put something very important here. Has to be with P of t and Q of t continuous on the solution interval. All you have to do to solve one of these, find all solutions, is to find two of them and write C1 times one plus C times the other. That represents all of them. So no longer do we have to solve this kind of equation by integration. We can solve it by finding two solutions and writing an arbitrary linear combination. Right? And by linear combination, I mean C1 times one plus C2 times the other is a linear combination of two functions. Right? So here's a really easy example that we've already been kind of looking at. Right? Suppose I consider the differential equation d squared y dt squared plus 4y equals 0, right? It's the same one we did before, y double prime plus 4y equals 0. we know that this has solutions. Y1 of t equals sine 2t, and y2 of t equals cosine 2t, right? And over there, we use the Wronskian to prove they're independent, right? By Abel's theorem. By the Wronskian, Abel's theorem. So what do we write down immediately? We write down the solution immediately. All we have to do is maybe guess two functions and put down this result. Y equals an arbitrary constant times sine plus an arbitrary constant times cosine. That gives us every solution to the differential equation. When we write it in this form, C1 times 1 plus C2 times the other one, representing all solution, we call it the general solution. Look at that, how easy it was to get the general solution to this differential equation. We just wrote C1 times one solution plus C2 times the other, and we're all done. Every solution looks like that. There's a beautiful, beautiful analogy in geometry. We talked about vectors in the plane, right? Suppose I want a plane of solutions in 3 space, right? Vectors in the Euclidean plane again, right? Suppose I want to find all the set of all vectors in this plane through the origin, right? Plane containing the origin, x, y, z. How can I write the general form of all vectors in this plane? How do I do it? Remember how to do this from geometry, maybe? Analytic geometry? One way to write all vectors in this plane is to take any vector you want in the plane, any non-zero vector. By the way, the zero vector is always linearly dependent. So just so the zero function is always a dependent. You can never have the zero function here. But here's a vector in the plane. Here's another vector in the plane. And I can get to any vector in this plane, say this one right here, this vector right here, other color. Maybe I want to get this vector right here. I can get it by taking a multiple of this one, maybe going out to here, 3/4 of this one, plus maybe 1 1/4 times this one. And so I take a multiple of this one plus a multiple of this one, and I add this one to this one, putting the vectors end to end, right? I get this one. This is maybe whatever, 3/4 V plus 5/4 W or something like that. The point is you can span all vectors in the plane with 2 vectors, right? If you have 2 vectors, every other vector in the plane is a multiple of one plus a multiple of another. Just so here, every solution to the differential equation is a multiple of this arbitrary one plus a multiple of this arbitrary one. We are spanning a 2-dimensional vector space of all solutions to the differential equation, it turns out. So just like explain this plane of vectors solutions to some geometrical problem, we're going to span the plane of all vector functions in a vector function space with 2 of them. So that's the analogy. Think of it like this, I think really helps. So a multiple of one plus a multiple of another gets you any vector in the plane. A multiple of one plus multiple of another function gives you any solution to the differential equation, right? So really interesting geometrical result. You don't have to integrate. How about that? This is a fun method like that. Let's see how much time I have to do this now. We won't do the proof of that theorem, it's too long. Now, the most important case, because these come up in real common applications in electronics engineering and classical mechanics and physics and lots of other places, but particularly in those two branches. We're gonna look at homogeneous, we're gonna narrow it down even more. Wake up with some scratching on the board here. Homogeneous. Maybe I won't. Gotta put some comic relief in here to keep. Homogeneous, linear, second order. Differential equations is what we've been looking at, right? We're gonna add one more restriction with constant coefficients, and now you can really see why we like to abbreviate these things. This, well, what is that? Here is a homogeneous second order linear equation. All we need is constant coefficients. That means you just replace P and Q with constants, and then you multiply the whole equation through a constant, and it's still the same. It's equivalent. So move this over here. So these are just equations like this. These are equations A y double prime plus B y prime plus C y equals 0. Homogeneous linear, and now you have constants instead of general functions. So I gotta watch my time here. Leaving once in a while. These have a great way of finding two solutions, right? What we just found is that any homogeneous equation, this is one, can be solved if you can just find two independent solutions, right? So how can I find two independent solutions to this? There's this really neat method, sort of a method of lucky guessing. Right? Well, let's do a test solution, they sometimes call it, to see if we can kind of guess here. Suppose I look for a function of the form y equals e to the RT, or r is a constant, right? If that's the case, it's easy to compute the derivative. Y prime would be r e to the RT, and y double prime would be r squared e to the RT, and using the chain rule for e to the RT. These test solutions plugged in, maybe it'll work. Okay, right? Because these are all multiples of the original e to the RT. That makes, when you plug these in, each of these terms a multiple of e to the RT. Maybe I can make them cancel. Right? Plugged in gives, what do I get? A times y double prime is r squared e to the RT. Plus b times y prime is r e to the RT. Plus y is e to the RT. And I need that to be equal to 0. So when I plug in this test solution, I get that equation. And now if I factor this all out, what I've got is AR squared plus BR plus C, all multiplying e to the RT. I just factor out e to the RT, have to equal 0. Well, e to the RT is not 0, right? E to the anything can't be 0. So I can divide through by e to the RT and say equivalently, for e to the RT to be a solution, it has to satisfy this equation, right? Because I plugged in. E to the RT is a solution if and only if AR squared plus BR plus C is equal to 0. I can solve that as a quadratic equation, right? We call this particular quadratic equation, though, the characteristic equation for this one. I guess I should call this 4. Characteristic equation 5, or differential equation 4. It's just a quadratic equation. If I can solve that, I can get solutions to the differential equation. What this shows, this characteristic equation shows, I just proved it, that y1 of t equals e to the r1t is a solution. And or if R1 and R2 are the solutions by quadratic formula, and Y2 of t equals e to the R2t, are solutions where R1 and R2 are the solutions to the quadratic equation. I know exactly what those are because it's a quadratic formula, right? Minus b plus or minus square root b squared minus 4ac all over 2a. Simple, right? All you have to do is solve this differential equation now is solve a quadratic equation from algebra, right? Right, e to the r1t or e to the r2t, and then you've got this great result. Now, one, if R1 is not equal to R2, are both real, then what do you know? E to the R1t, e to the R2t are solutions, and y equals C1 e to the R1t plus C2 e to the R2t is a linear, arbitrary linear combination of two solutions is the general solution. With one disclaimer, right? These have to be independent solutions. Are they independent? You don't want to check it every time, but it turns out that Wronskian shows that unless R1 equals R2, these are independent. So that's why I put this disclaimer up here, R1 not equal to R2. If R1 equals R2, then they're the same function. They're one times each other. They're dependent, right? But if R1 isn't equal to R2, you can put this in the Wronskian, show these two functions, e to the R1t and e to the R2t are independent. This is all solutions immediately. It's as easy as that. And one more disclaimer. Have to be real. If they're imaginary, either imaginary number times t gives you an imaginary result. So actually, that's of use when you're solving differential equations for complex solutions, and those are useful in engineering and other practices. So we are going to consider the imaginary case and the equal case. They will come up with real solutions, it turns out later. But for now, we'll say if they aren't equal and real, then you get independent solutions. There's the general solution. That's all there is to it. Not great. It's easy to solve that. I want to do a simple example. Boy, I'm trying to right for a change. We'll get some useful result today. I'll erase this now. Here's a simple example how easy this makes it. Suppose I asked you to solve, find the general solution, and then if you apply two initial values, it would find a unique solution. We'll just find a general solution, the form of all solutions. Of this easy differential equation, y double prime plus 4y prime plus 3y equals 0, right? This is of the form 2a, a linear, well, let's say a form 5. The case of equation 5, linear homogeneous with constant coefficients of second order. So we're going to apply our technique we just learned, right? We're going to say this. First thing you do is you write the characteristic equation that corresponds to it. How easy is that? It's this easy if you look at that for a second. All you do is you replace the derivative with 1 r and r squared respectively. You take r squared replacing y double prime, r replacing y prime, and 1 replacing y, and you write that. The characteristic equation you write down by inspection. How about that? There's the characteristic equation. Now you can solve this with the quadratic formula if you want, right? That's a good way to find R1 and R2, but what's an easier way to solve this one? Even easier than the quadratic formula, it's just a formula, right? There we go. I knew somebody took algebra. Yeah, next one. R plus 3. R plus 1 is an obvious factoring thing, right? The factor is equivalently like this. So R1, the first solution, is minus 3. R2, the second solution, is minus 1. I'm just trying to wake you up. Okay. So those are the two solutions by inspection. Now, 2 I know two independent solutions immediately. Y1 equals e to the minus 3t. Y1 or Y1 of t, it doesn't matter. I get tired of writing of t all the time. Y2 equals e to the minus 1t are independent solutions. We could check the Wronskian, but we don't have to. When R1 is not equal to R2, it's easy to prove that it's always independent just by putting in a general R1, R2. So we'll say they're independent solutions. We can check the Wronskian, but we don't want. Since R1 equals -3 is not equal to -1, which is R2.
Can you move the camera a little bit?
Oh, yeah, thank you. They're like Newton with his horse. I told you one, was thinking about this bath pile. He had to get off his horse and walk it up the hill, and he got up the hill and realized his horse had run over on the other hill. He hadn't been paying attention. He's just holding the rein the whole time. Anyway, all right, so we're, so now step 3 is y equals C1 e to the minus 3t plus C2 e to the minus t, where C1 and C2 are arbitrary real numbers. Represents all solutions. The solution is a vector space of functions spanned by these two functions. Easy as that. These are very important. They come up in lots of, like I said, I told you, classical mechanics for vibrations of simple structures and so forth. They're elementary model, very important. All right, so there's the general solution of that one. Looks like I've got 1 minute left, so maybe I should just maybe just quit there, huh? All right, I'm gonna do one more. Let's try this. I don't think we can do all the problems in the latter section, but you can do the ones where R1 and R2 come out to be real and not equal. The ones where they're equal or they're imaginary complex conjugates, we'll have to do next time. That'll be a good topic. So that'll be our topic for the video lecture next time. Will be what if R1 and R2 are equal? What if they're complex conjugates? You can't get other complex numbers because the quadratic formula shows you that if you have a quadratic equation such as this one, any complex solutions come in conjugate pairs. So we'll only have that one case. Here's some homework then to look at. Look at 3.2 out of the notes. Numbers 1 and 2. Those you should do both of those. Those are on the preliminary material we did with the Wronskian and independent solutions. And then 3.2.2, that is, I'm sorry. 3.2.3. Numbers 1, 2, and 3. Probably do like 1A and 1B or something like that, where it has not equal real solutions. See if you have any questions on that. We'll talk again on Thursday then. Thank you so much for your attendance today. It's a lot of stuff in this.
Yeah.
15-minute class is much better. Let it sink in.